Our first differential equation is the population equation. It describes how population of humans grow. So, let's first think about the population of a country. We can say that population is a function of time because it changes over time. But let's say we don't know what the population function is. Instead, we can describe it as change. The change of population is proportional to the current population. That can be written as dp dt is approximately pt. So the change in population is approximately the population. In the tutorial, we'll work through the differential equation to get a feel for a simple differential equation, but this of course will generalize. So let's begin. Let's assume the change in population is equal to the birth rate alpha times the current population. So the derivative dp dt is equal to alpha times pt. Change in population is equal to birth rate times current population. It makes sense. Population change is some kind of formula like that. So let's plot that. Not solve. Let's plot the population as a function of change in population. And the example here, I'm going to say the birth rate is 0.3. So what we see here in the graph is the x-axis is population, y-axis is change in population. And we see a straight line. The larger the population, the larger the change in population. It's intuitive. To solve this kind of differential equation, we need something called an initial condition. So, the population differential equation is not enough to model the population alone. We need to know the population at a time point, our initial condition. So, pt0 is equal to capital P0, or at some time point t0, we know the population. Generally, mathematicians just say t0 is equal to 0 because it's simpler. It gives you the same answer. We can integrate our solution, and that gives us P0 e to the alpha t minus t0 is the population equation. But in a simple example, let's say the initial population is 1, and let's say our time period is 0. So then pt is equal to e to the alpha t. That's where the term exponential growth comes from. So it's exponential growth as a function of the birth rate. So these kind of equations, specifically this model, has some strengths and weaknesses. It has an exact solution, which is great, and that's great for learning. It's easy to interpret. It works some of the time. So that means that this kind of population model is okay, but it can break. And why does it break? Because one, it does not take into account such things as limited resources, like food. It does not take into account external factors like wars. And it does not take into account a dynamic change over time of birth rate. The dynamics are static over time, so you can't change birth rate. It won't grow over time. But still, it's a good equation to start with. And always remember that. These equations are normally good equations to start with. Your exercises are 1. Code and plot the rate of change of the population as a function of the population. Code and plot the population exact solution of the function of time. There you can see the relationship between alpha and the solution. This is going to be very important because sometimes we won't be able to know the exact solution, but we'll be able to understand what it should feel like and what it should look like just by looking at the derivative.